Okay, hello everybody. This video is a summary of chapter 7 to help you study for it. We'll go through the learning objectives one by one and see what they mean. The first paragraph is about what is a force and how is it related to velocity. A force basically is a push against something or a pull. And then it is measured in Newton. So the more newtons, the harder you are pushing. Most common idea is that you require a force to move something. However, this is not completely true. You can tell from this simulation there's a guy here who will start pulling the car as soon as I press go. Okay, there he goes. So he starts giving the car speed now, and now I will remove him. The car is not losing speed now because there's no force working on it. I'll let it return, and this time give a little speed. I'll remove the guy. And I'll add another guy on this side. And now the car starts losing speed, and now it starts gaining speed in the other direction. But the force is to the left all the time. And if I add 2, now the force to the right is larger. So you will see the speed will drop again. Hopefully on time. Nope. He will pass. And yeah. Yes. They reduce the speed to 0, and then they start increase it to larger numbers to the right again. So you do not necessarily need a force to move, but you do need a force to change your speed. When I remove all the guys, then there's no force working on him anymore for some reason. Yeah, and the speed will stay constant. So that's an important lesson here. Changing speed requires force, and if there's no force, then the speed is constant. And that can mean 0, because 0 meters per second is also a constant speed, just the speed of 0, but it could also be 2 meters per second or minus 3 meters per second. In this case, the minus simply means the car is moving to the left instead of to the right, which would be plus 2 meters per second. But it is still constant. Paragraph 2 introduces a formula to calculate, for example, what speed an object will get when you are pushing it with a certain force. So here's the formula. This is the force, or actually we would say this is the sum of force, because if I have more forces working on an object, for example I have a box and I have one person pushing it to the right and one person pushing it to the left, but the force to the left is smaller, then the force that needs to be filled in here is the force of these two together. So that would be a little bit smaller because the force to the left cancels part of this force. So the sum of the forces will indicate how much acceleration you get. So that's you need to put the sum of the force in the formula. Measured in Newton, of course, multiplied by time in seconds, and this equals the mass in kilogram times v end. That's the speed in the end after the push, measured in meters per second, minus m times v begin, also in meters per second, and of course also the mass in kilogram. When you are accelerating an object that is standing still at first and then starts moving quicker and quicker, so that would be for an object with a VT graph that looks like this. 0 at first and higher later on. Then the formula becomes a little bit easier, because here this is v begin and v begin is 0. So if I fill in 0 here, then this part drops out and I get f times t equals m times v end. Okay, so this is the formula during acceleration, speeding up. The formula is also perfectly useful when braking. So to show you how that works, I'm going to write the formula in full first. So m times v end minus m times v begin. This time of an object that brakes until it stands still, the VT graph looks more like this. It starts out high and after a while it becomes 0. So v begin is now obviously not 0, but v end is. So now this part of the equation drops out and I am left with this, minus m times v begin. Now you might wonder, what's that minus sign doing over here? Well, it was there to begin with, but if I would fill it in without thinking, I might all get negative numbers. The trick here is when an object is slowing down, it is moving to the right, but there's a force working on it to the left. So this arrow indicates its speed, which is directed to the right, but the force is in that direction. This, for example, if it would have a speed of plus 2 meters per second, then I would need to indicate the force as a negative number, for example minus 5 Newton, because to the right is plus and to the left is minus. And if I do this consistently, then the minus sign disappears, because I'm filling in a negative number over here, and the minus sign makes this side also negative. It is usually easier to just ignore this, so you can work with the formula like this and fill in positive numbers in for every symbol. This allows you to calculate braking distance of an object, but you need some extra formulas to do this, because you can calculate the covered distance using S equals V average times time. However, with this formula you calculate V begin and not V average. V average can be calculated by taking V begin plus V end and dividing by 2. When this is the case, you're braking to a standstill. It becomes even easier because V end is 0. So you get V begin divided by 2 and the V end disappears. There's also something special about this equation that I need to talk about. That's the right part of it. This part. This part is also known as momentum. the symbol for momentum is P, and the unit of momentum is kilogram times meter per second, because you're multiplying mass with speed. And basically these are the properties of the object itself, its mass and its speed, and the quantities to the left are the factors that are working on the object, the force and how long the force is working. And this basically shows that when you have an object with a high momentum, it takes a large force to stop it, or small force for a long time. If you have small momentum, this can be done with a smaller force, or you don't need to push as long. Then about the braking path. This shows clearly how they can calculate braking path. However, you also need to take into account that when you're braking, you also need time to react. For example, when you see a car crashing in front of you, then it takes you a little while to realize you need to stop and actually start pressing the brakes. And all that during that time your speed doesn't change. Sure, your VT graph will look like this, and only when you've started pressing the brakes your speed will drop. So when you need to calculate not the braking distance but the total stopping distance, you also need to take into account that little bit. So you need to know reaction time, which is in the order of milliseconds. For me it was about 200 milliseconds. And then calculate with S equals V times T the distance covered in that part. So this will give you the distance covered during reaction time, and this is the distance covered during braking, and then the total distance is simply these two added. Okay, the last paragraph 7.4 will not be part of the test, so this concludes this video. Good luck to you all studying, and see you all in class.